For the final part, Part D of Homework 4 for process dynamics and controls, we are getting into cascade control. So I'm going to explain just in general how cascade control can be used, and I'm going to draw some block diagrams, and we'll end with a code kind of similar to the last video. We're going to start off with explaining how cascade control could be used to enhance the control of an exothermic reactor by adjusting the flow of makeup cooling water in its recirculating cooling jacket. So cascade control consists of two nested feedback loops, a primary/master and a secondary/slave. The primary adjusts the set point of the faster secondary loop, and that improves our disturbance rejection. So disturbances have less effect on the system. And our secondary loop uses an intermediate variable, and that reduces the effect of time delays. So we would have some tank. And this tank will have a temperature sensor. And we said that this is a jacketed tank. This reaction that we're performing in this tank is exothermic, so we have to send cooling water through the jacket. And it's continuously recirculating so that the temperature stays more consistent throughout the jacket. So what we have from here is a temperature in. This is what can have our disturbances possibly. Goes into our jacket. We obviously have a temperature coming out, and that is the temperature of the jacket that I'll refer to as TJ. And then this right here is the temperature of the jacket. We have a recirculating pump. And we have a jacket controller of some sort. And so that's kind of what we're looking at, but we would like to I want to show what this looks like with cascade control. Basically, you would have a set point going in to the system. You would have a comparator. You would have your primary controller or the master controller. That also goes to a comparator into the secondary controller. That goes into the secondary process. Again, we have our disturbances. Compare that. Finally, into our primary process. And I should say that this disturbance is the inner loop disturbances. And then we are also going to have the outer loop disturbances. I'll call that GD2 for now. And then we get our output. And we have a loop from right here to this comparator. We also have one from this arrow pointing to the output to our first comparator. So this right here would be our secondary process variable. So for example, this could be cooling water flow for our jacketed tank. And this would be our primary process variable. And this would be the reactor temperature itself. So I think in my picture up here, basically what we can see from this is if we're looking at the temperature in this cooling jacket, that's a faster turnaround time to get that temperature than this temperature sensor at the top. That might be a little bit slower. And now I would like to draw the block diagram for part D1 more thoroughly and derive transfer functions that relate the reactor temperature to changes in the set point and disturbances in the inlet cooling water temperature. So we would have a reactor temperature set point, so that's TRSP, going into a comparator. We have the TR controller, which is the master controller, or the primary controller. Going into another controller, into a jacket temperature controller, which would be the slave controller, or the secondary controller. This goes into our jacket. We have a comparator, disturbances from the temperature going in, going to our reactor, and our reactor temperature output. And as before, we have a loop here. That's our inner loop, and one all the way out here. And I'm going to call this TJ controller GC 1. And this jacket is the transfer function I'm going to call GP1. Similarly, our reactor temperature controller, I'm going to call that GC2. And the reactor transfer function will be GP2. As you can see, we have an inner loop right here that we're going to call the servo. And so a transfer function should be the forward direction divided by 1 plus everything in the open loop. So we get TR is equal to GC2 right here, up there, GC2. And I am calling this inner loop servo, so that's going to be I'm going to label that G servo. But just know that that would be GC1 and GP1 included in that. And also in the forward direction we have GP2 divided by 1 plus everything in the open loop, which would be GC2, G servo, GP2. This gets multiplied by our set point, but we need to remember we also have those disturbances. So we have our GD times GP2 because we're starting up here. We don't include anything previous. So we have GD times GP2 divided by 1 plus the same thing as the previous, and that is multiplied by the disturbance coming in. So this right here is the transfer function that we calculated. And that relates the reactor temperature to changes in the set point and disturbances. And now I'm going to go ahead and get into the code. We want to simulate the unit step disturbance, rejection, and set point servo control for the following cascade control system. The inner control loop process that we defined as GP1 is as follows. Proportional only control, where that gain is 1. Our disturbance transfer function as follows. Outer process transfer function as follows, and the outer PI control gain is also 1, and we're using a reset time of 1, so our tau. As always, I started with my import, and I'll just get started with defining our variables. So we said that KC1 is 1, KC2 is also 1, and our tau is 1 as well. That's our reset time. And from here we're given those functions, so I'm going to copy that so I can just hopefully easily paste. We have GP1 is equal to 1.5 divided by 2s plus 1, and our GD1 is equal to 1 divided by 2.5s plus 1. Our outer process transfer function is 1 divided by 20s plus 1. That's GP2. And I'll need to include a multiplication sign here so that they know, so that the code knows what I'm talking about there. We're setting our GC1 equal to KC1, and our GC2 is equal to KC2 times 1 plus 1 divided by our tau times s. So for the open loop transfer function of the entire system, I'm going to call that beta, and that's equal to GC2 times GC1. Remember, I called this servo when I was writing this down, but GC1 times GP1 times GP2, all divided by 1 plus GC1 times GP1. And for our disturbances, I'm going to call this alpha. We have GD1 times GP2 divided by 1 plus GC1 times GP1. First, we're going to look at disturbances to the inner loop. So I'll just call that DIST for the disturbance. Alpha divided by 1 plus beta. Lambda, N, and DT. We want to make our subplots, add a scatter with x is equal to t, y is equal to our y disturbance. Our mode is lines, and we're going to set a width and a height and show our figure. So basically we have our disturbance and our system oscillates a little bit, but because of our servo control for our cascade control, cascade controlled system, it levels out relatively quickly after only a couple minutes at basically 0. And now we want to look at the outer loop disturbance. Or sorry, I said outer loop disturbance. What I meant was I guess it's the same thing, but looking at an outer set point change. So if we changed that reactor temperature set point at some point. We already have all the needed information above, so we're going to do a new simulation where if the set point changes, we again have beta. Actually, this time it's beta divided by 1 plus beta because we're looking at the outer loop, not the inner loop. Specifically, lambda t are same n and dt values. And we'll go ahead and make our subplots, add a scatter where x is equal to t, y is equal to y set point. Our mode is lines. Same layout as before, so we can compare much easier and show the figure. And then we see right here, this is how our system behaves when we have a set point change. So this was disturbance changes, so that would be changes in the cooling water coming into the jacket, and this would be if we changed the reactor set point. So obviously, if either of those change, we want our system to respond relatively quickly, which it does in both of these cases. So these oscillations are probably because maybe our gains are too high or something needs to be altered, but overall we reach steady state relatively fast. And because we're using cascade control, we can respond to both those the disturbances in the cooling jacket water as well as changes in the reactor temperature set point. And that is everything I have for this video, as well as for this class. I'll probably be uploading the separations videos after this, but I am recording this after those, so this is kind of my closing out. But thanks for everyone that's been watching. Especially want to shout out my grandfather. I know he's been watching all of my videos, so thank you for that. And thank you to my professor for teaching me all of these interesting concepts. I don't know if I'll be uploading to my YouTube after these classes, but we shall see. Again, thank you very much, and hopefully I remember to edit a photo or video of my cat at the end of this video as well. So hopefully you look forward to that. Thank you.